Before we move on, exactly what is radiation? Well, it was Ernest Rutherford and his associate, the brilliant Nobel Prize-winning physicist Frederick Soddy, who discovered the true nature of radiation. Now, gold doesn't radiate, does it? I mean, either does aluminum or oxygen for that matter. Neither does silver or copper or lead. No, all these elements, when sitting by themselves, behave themselves quite nicely and don't radiate any mystery rays of any kind that we know of. But these other elements like radon, radium, and later polonium, francium, uranium, and plutonium, they don't seem to behave at all. All on their own, they radiate these weird rays, and the elements eventually break down into simpler, less complex elements, especially lead. Francium, for example, is very radiation active and also very rare. The biggest clump was about 10,000 atoms, not very big. But if you could get a big clump of francium together, this is what you'd see. In about 20 minutes, half of it will break down into radium, astatine, and radon. Then if you keep watching, the radon itself would continue radiating these rays until in about 3 days, it would fall apart into polonium, bismuth, then lead. Meanwhile, the original clump of francium is continuing to break down. Lead doesn't radiate anything. And this goes on and on and on until all the rays are finally spent, and all you have left is a couple of well-behaved, stable elements, usually lead and bismuth. Francium decaying by radiation is called radioactive decay. Here's a fruitful analogy. Imagine that you have a watermelon. Suddenly, and for no apparent reason, one of the seeds comes flying out through the thick skin. Then more seeds and more seeds. It's radiating seeds. Soon you find that half of the watermelon has turned into a smaller cantaloupe, and the other half of the watermelon still spits out seeds. The cantaloupe is also radiating seeds. And after a certain amount of time, half of the cantaloupe turns into a smaller grapefruit, and seeds radiate out of it. Meanwhile, the watermelon has again become half a little cantaloupe. This goes on until half of the grapefruit turns into a stable apple and finally a stable orange. No seeds come out of the apple or the orange. This is the strange case of decaying fruit, with bits flying out of the fruit until it finally becomes a more stable apple or orange. It may take seconds or days or years or centuries until it finally stabilizes. Now, this is odd behavior for fruit. And fortunately, fruit doesn't behave like this, and neither do most of the elements. But some of the elements behave exactly like this. They start off as some big ol' heavy watermelon-size element like uranium and start throwing off bits of themselves until they finally transmute into some simpler, more stable form like lead or bismuth. The amount of time that it takes for half of that element to transmute into another element is called its half-life. It may take seconds or fractions of a second to decay like this. Some take days or weeks, years. Some never stop radiating, or practically never. This chain of events decaying into simpler forms is called the decay chain. This is the decay chain of uranium. It decays through all these other elements until finally becoming the stable isotope lead-206. Exactly why some elements do this, we will discuss in an upcoming segment. We've just about arrived at the periodic table of the elements. All that was needed was some accurate way to organize it, and here was just the man to do it. This is the only known picture of Henry Moseley taken in the laboratory. He died near the Aegean Sea only a few months after this picture was taken. He was 27. Like so many other brilliant scientists at this time, Henry Moseley was a student of Ernest Rutherford and belonged to Rutherford's research group. By Moseley's day, the beginning of the 1900s, it was well known that when the elements are exposed to fire, their gases give off a distinct fingerprint of color. Here is sodium on the left giving off a distinctive yellow color, and copper on the right burning a greenish-blue color. By using a prism, every element can reveal their distinct fingerprint in the color spectrum. The prism breaks up white light from the sun into the colors red, orange, yellow, green, blue, indigo, and violet. Examining the light spectrum like this is called spectroscopy, meaning to examine the spectrum. By fitting a couple of prisms together in a tube, along with a couple of lenses, you get a spectroscope, which means it works like a telescope, except that it sees the fingerprint of the light spectrum. Here is the light fingerprint for the whole spectrum. Here's the light fingerprint for helium, for hydrogen, and for gold. Even sunlight has a unique spectroscope fingerprint, but a high-resolution spectrometer is needed to see the detailed fingerprint. The barcode-like image shows an abundance of hydrogen, plus some helium and sodium. It was also known that by using Wilhelm Röntgen's X-rays, every element gave off a distinctive X-ray fingerprint, and Moseley began bombarding every element he could find with X-rays in order to discover its unique X-ray fingerprint. By carefully analyzing these lines, Moseley found a pattern. And here is the chart of his findings. As the X-ray lines progressed element by element, so the positive charge of each element increased by 1 as well. Again, Moseley found a direct link that as the positive charge of each element increased by exactly 1, so each X-ray line stepped up by 1. Now, what is it in an atom that could increase by exactly 1 that would also increase the positive charge by 1? Not electrons, they're negatively charged. What about Ernest Rutherford's hard nut, the nucleus of an atom? Yes, and that was Moseley's answer. Moseley discovered that every element changes into the next element when a positive proton is added to the nucleus. So, you start with hydrogen, the lightest element, because there's only one proton in the nucleus. Add a positive proton and, incredibly, it turns into helium. Add another proton, the element is lithium. A fourth, it becomes beryllium, and so on. One positive charge at a time, all the way through the amazing periodic table. Moseley proved that it is the positive particle in the nucleus that determines what an element is made of. Suddenly, we understand what part of the atom is responsible for turning every element into a new element, the positive protons. And we have an easy, elegant, and scientific way to number and organize the periodic table by the positive charge in the nucleus. Thus, hydrogen has one proton, and so is given the atomic number 1. Add a proton, you get atomic number 2, helium. Add another proton, it turns into lithium, atomic number 3. With 8 protons, you get atomic number 8, oxygen. 29 protons, copper. 79 protons, gold. The atomic number is the number of protons in the nucleus of the atom. Prior to Moseley, the elements were sorted according to their weight, and nobody really knew how many elements there were because there are varieties of elements, which we will see in a moment. Even Mendeleev put them in order of weight, which was very close, but not exactly like Moseley's perfect progression of 1 electrical charge per element. Now we knew exactly how many elements there were, because you can't add 1½ protons. You add 1 at a time, and Moseley's X-ray chart proved that as each element progressed, so the electrical charge also stepped up by exactly 1. It was the electrically positive protons that changed an atom into the next element. The system was so precise and elegant that Moseley, like Mendeleev before him, was able to predict many elements that had yet to be discovered. Namely, those with atomic numbers of 43, 61, 72, 75, 87, and 91. They were unknown in Moseley's day, but all were found in due course. Spectroscopy was responsible for finding nearly 20 elements in the periodic table. Moseley's research, even in his day, was recognized as brilliant and of the highest scientific order. Had he lived, Moseley no doubt would have won the Nobel Prize for his research. Unfortunately, his scientific career lasted only 40 months. World War I broke out. He served on the beaches of Gallipoli, a narrow strait of water by the Aegean Sea in Turkey. He was killed by a sniper's bullet while telephoning a military order. The physicist Robert Millikan lamented, "In a research which is destined to rank as one of the dozen most brilliant in conception, skillful in execution, and illuminating in results in the history of science, a young man, 27 years old, threw open the windows through which we can glimpse the subatomic world with a definiteness and certainty never dreamed of before. Had World War I had no other result than the snuffing out of this one young life, that alone would make it one of the most hideous and most irreparable crimes in history." Near one burial site in Gallipoli, Turkey, is the Cape Helles Memorial. Among the 21,000 names of men who died in that battle, there is the name of Henry Moseley. He has no known grave. It was a great loss for science, but a great gain also. Because of the work of Henry Moseley, science now had a definitive method to assemble the periodic table. As one proton is added to the nucleus, the element gets heavier and periodically progresses. Now let us quickly recap everything we've seen that brought us to this point. Early metalsmiths like Tubal-Cain learned the art of separating and joining together. Robert Boyle and Antoine Lavoisier broke loose from alchemy and set us on a serious scientific path. John Dalton gave us the first hint that atoms existed and actually weigh something, and were probably like solid billiard balls. Using Volta's new battery, Humphrey Davy and Michael Faraday developed electrolysis to separate out new elements. As new elements poured in, John Newland saw a pattern of 8s in the elements, just like in music, which Dmitri Mendeleev also noticed and boldly developed the first periodic table based on atomic weights. At the same time, William Crookes was busy inventing the cathode ray tube, which J.J. Thomson used to discover the electron and develop the plum pudding model of the atom, and which William Röntgen and Ivan Poluya used to discover X-rays. Henry Becquerel was experimenting with those same new X-rays when he accidentally stumbled across radiation messing with uranium. His colleagues, Marie and Pierre Curie, greatly expanded on Becquerel's work and discovered the radioactive elements polonium and radium, while at the same time over in England, Ernest Rutherford used some of Curie's radium to make an atomic ray gun and discovered there is a nucleus in the center of an atom. Finally, Henry Moseley, in a brief and brilliant scientific career, takes Röntgen's X-rays and Mendeleev's early periodic table and rearranges the elements according to the number of protons in the nucleus, which forever after is known as the atomic number, or the proton number. What an amazing journey it has been, but at long last, the work of all those brilliant men and women have finally brought us to this. the modern periodic table of the elements. But what does it mean? And how is it organized? And how do you read it? That will be the discussion of our next segment.